Howdy. Today I'm going to be doing exam 2 2017 for Physics 207, and I'm going to try my best to explain it so everything will make sense after this exam, hopefully. So, if we start with number 1, in the circuit below, we're told that R's, C's, and V's are unknown. The circuit was put together a long time ago, meaning we're in steady state, and it's asking us to find the currents in each resistor and the charges on the capacitors. So before we even begin solving, we have to first define our current and label the charges on our capacitors. So I'm going to start on the positive battery, the V1. I'm going to call my current I that flows through the circuit. And then I have a junction here, but it's not really acting as a junction because we know in steady state, no current can flow through the capacitor. So in reality, my I is only flowing upwards. And I continue this path until I get to this bottom junction where again, my current cannot go to the left because there's a capacitor. So it's the same current that only goes down and no current goes in that left path. And I reach back my battery. And the next thing to do is label the charges on the capacitor. So I'm going to say that this is plus Q1, this is minus Q1, this is plus Q2, minus Q2. This is very important because even in the question it says if you don't label the charges, you're not going to get any credit. So after that, I can just write the loss. The loss for practically any circuit is going to be these two, where if we go along a closed loop of E dot dr is equal to 0, and in the second row will be the junction rule, where the flux of J dot ds is equal to 0. But in this case, we don't really have any junctions, so that won't really be of any use here. But it's always good to write down. And then occasionally, we will use conservation of charge, but I don't think this exam will cover that. So the application will be, well, I haven't even defined my loops, so let me do that first actually. So there are many ways you can choose to define your loops. So the way I'm going to do it is I'm going to write a big loop across the outside of the circuit. Call that loop 1. I'm going to have a smaller loop within the top right rectangle. Call that loop 2. And then I'm going to have another smaller loop in this bottom rectangle. Call that loop 3. So if I do loop 1, solve for loop 1, if I start at this green dot for loop 1, I'm going this way. I'm going to the right, current's going to the right, so it's going to be positive. So I'm going to first have IR, and then I'm going up, and again, I'm going the same way as my current. I is the same because there's no junction, right? No current in the capacitor. So then it'll be a plus another IR. I continue to go down, or go to the right of my circuit and then come down. And I keep going down because I'm going on the outside. And now when I'm at the bottom left, I'm going to the left and current is going to the left. I is still the same and the resistors are. So that's plus another IR. And then I come back and I touch, when I'm down here, I touch the bottom part of the battery, which is the negative side. So minus V1 is equal to 0. That'll be my first equation. For my second loop, let's start here at this green dot. I'm going this way. So I'm going to the right, current's going to the right. That'll be IR. And I come down and then I touch what I labeled the negative part of the capacitor. So, and we're finding the difference in voltage, right? Recall that a capacitor is Q over V, where voltage is Q over C. In this case, I'm touching the negative part of the capacitor. So that'll be minus Q1 over C1. And I'm back at the resistor, so that ends my loop. So that's equal to 0. Now for the third loop, I will start, let's see what my red dot is. I'm going in this way. So I'm going to the left, current's going to the left. So I have positive IR. I come up and then I get to that resistor. But again, there's no current that's flowing up there because again, current can't flow through a capacitor. So we basically disregard that resistor. But then the capacitor still has charge on it. So we put plus Q2 over C2 because I'm touching the positive side, or what I label the positive side of the capacitor. So that's plus Q2 over C2. And then I keep going. I touch the positive side of the battery. right? So that'd be plus V2, and this would be equal to 0. So if I look at what I have I, which is unknown, Q1, which is unknown, and Q2, which is unknown. And I have 3 equations. 3 equations, 3 unknowns. This is more than enough to be able to solve this problem. So loop 2 is actually pretty easy to solve because I get Q1 is equal to C1 IR. Right? I just moved over the IR to the left. So I have 2 negatives. Negatives drop. I multiply by C1 on both sides. And that gives me Q1. Now for my second loop, I will have Q2. I need to solve for Q2, right? And I plan on using the top one to solve for I. So I have Q2 over C2 is equal to negative IR minus V2. And then solve for Q2, just multiply by C2 on both sides. So let me actually pull the negative out. So negative C2 IR plus V2. Now that I know what Q's are, I can make a substitution into the first equation, and I can solve for what my current is. So the current is the same for all 3 of these resistors, and R is the same for all 3. So I'm basically adding 1 plus 1 plus 1, which is 3. So when I add those, I have 3 IR minus V1 is equal to 0. So I move to the right, with the V1 to the right, so I get IR equals V1, and divide by 3. So I actually didn't need to use Q1 and Q2 to make a substitution in number 1, because there was no Q1s or Q2s in the equations. If I would have written my loop, so let's see, if I would have written my loop on the inner side of the circuit, then I would have to make the substitution. But because I went along the outside of the loop, it was pretty simple to solve for. Oh, I forgot an R. It should be just I. It was pretty simple to solve for the currents. And then the bottom part is basically just asking you to plug in numbers to the equations you have. So if I do that, let's start with current. So current would be V1, which is 12, divided by 3 times the resistance, which is also 3. So this is 12 over 9. Yeah, 12 over 9, which could simplify to 4 over 3. So now if I solve for Q1, Q1 is C1, C1 is 2. My current is 4 over 3, and my resistor has a value of 3. So the 3's drop, 4 times 2 is 8, and that'll be the answer. Now for Q2, I have negative C2, which is 4, current, which is 4 over 3, times R, which is 3, which is 3, plus V2, which is 2. So this goes away, so this is negative 4 times 6, which is negative 24. And then having a negative answer just means that the initial guess I made with the plus Q and minus Q was flipped for the second capacitor. But that doesn't mean it's wrong, because with the way I define my capacitor and the way I define my direction of current, it makes sense. So it's still a right answer. Just because you have a different sign than suppose like what the answer key has, it doesn't mean it's wrong. It just means the way you did it, you got a negative answer. And vice versa. The answer key got a negative answer and you got the positive answer. It just means that the way you did it was different. Hopefully that made sense. So now if I go to the second problem, it's another circuit where R's and V's are known as well. The circuit was put together a long time ago, again, steady state. All of exam 2 deals with steady state circuits. And it wants us to find the current in each resistor. So again, we just define our currents and our charges on the capacitors. There are no capacitors here, so I'm not defining any charges on that, right? But I'm going to define my current. And when we have multiple batteries, like in this case, we just choose our favorite battery. So in this case, I would prefer to start on the top. So I would have current I flowing. And then there would be a junction here with I2 flowing and let me label I2 down here because resistor R2. And then I3 up here. And you may recognize that this circuit will get shorted out, but in case you don't know, we'll prove that, how we can get that. So down here, the currents meet again, right? So they merge into regular I again. And I just go around the entire thing, which is I, the remaining parts. So the laws will be the same as the previous question, where the closed loop of E dot dr is equal to 0, and that the flux of J dot ds is equal to 0. And this is basically another way of writing the junction rule, because that's what this is saying. So my rule for the currents that I defined will be I is equal to I2 plus I3. And now I need to create loops that covers the whole circuit. So I'm going to create my first loop on the inside rectangle, and then my second loop in this small square. So if I do loop 1, let's say I start at this green dot and go this way. I'm going to the right, current's going to the right, so it's positive. So it's plus IR1. And then I come down. Now I have a junction. So now instead of I actually have I2. But I'm going down, current's going down, so it's still positive. But it's plus I2R2. And then when I get to the bottom, it merges again. And then I go to the left, and I have plus IR3 because I'm going the same way as current. And then I touch the positive side of the second battery. So that's plus V2. And then I go up, and I'm going the same way as current. So it's plus IR4, right? Because the current get combined again. And then I touch the negative part of the battery when I get to the very top. So it's minus V1 is equal to 0. And then for my second loop, if I start on this red dot, I have a current I3, but it never comes into contact with any resistor at all, right? So for that section, this red section where the I3 flows, it has a resistance of 0, right? And then when I go up now, I'm going the opposite direction of my current because I defined I2 as coming down, but I'm going up. So that's going to be negative I2 R2 is equal to 0. So we have 3 equations, 3 unknowns. We should be able to solve this. So the easiest thing we can probably do is do the second loop right now, because I will get 0 minus I2 R2 is equal to 0, meaning that if I divide by R2 on both sides, I get to the current I2 is equal to 0. Right? So then, if I now work with my junction that I had up here, I know I2 is 0, so I have I is equal to 0 plus I3, meaning I is equal to I3, and that makes things so much easier to solve now. So if I work with my first loop now, let me box this in. I will have IR1 plus I2R2, which I know it's 0, so that just goes away, plus IR3 plus V2 plus IR4 minus V1 is equal to 0. I can combine, I can pull out an I and just add up the rest. So I will have R1 plus R3 plus R4. If I move the batteries to the right side, I will have V1 minus V2. And to solve for current, simply just divide. So I is V1 minus V2 divided by R1 plus R3 plus R4. So if we didn't note that this portion of the circuit got shorted out, that's how you could prove it. By doing the loop inside, no resistance in I3, it goes to 0. I2 minus R2 is equal to 0. Therefore, the current is going to be 0 for I2. Then we use the junction rule to come to the conclusion that I is equal to I3, which solves for I3 as well. And then we solve for the first loop, and we get our current is V1 minus V2 over R1 plus R3 plus R4. Yep. And then the second part is just asking you to plug in numbers, but that is pretty easy to do once you have the equation. So I'm just going to skip over that part and go to some more challenging problems that aren't circuits. So for number 3, we have a negative charge negative Q that is uniformly spread. So this right here tells me it's an insulator. It's uniformly spread. In a spherical shell, it's always important to see if it's a sphere, cylinder, or like a plane. In this case, it's a sphere. So with inner radius A and outer radius 3A, we want to find the difference in electric potential between the center of the shell and a point, a distance 2A. So I say like here, yes, like a point 2A right here. So this is going to involve Gauss's law to find the electric field. So the flux of E dot ds is equal to Q enclosed over epsilon naught, and the difference in electric potential, which is V of R2 minus V of R1 is equal to the negative integral of R1, R2, E dot dr. And that should be every rule we need for this. So I'm going to start where R is less than A. So my Gaussian surface will be in here currently. So in this region, the electric field is going to be 0. Why? Because our charge is distributed on the shell, like the actual shell. But in the inside, it's hollow, and there's no charge present at the center, so it's 0. If it had a charge like Q in there, for example, then it wouldn't be 0, because we would treat Q as like a point charge, essentially. But because the charge is on the shell, and the inside is empty, the electric field in that Gaussian surface we enclose is 0. So now, what if we're in between A and 3A, which means my Gaussian surface will be, this is red, it's going to be in green. So I'm in here now. So now I am inside where the charge is contained, so it's not going to be 0. So it will be the electric field, right, treated as a constant, and then the area of my Gaussian surface, which is a sphere, which is 4 pi r squared, is equal to 1, or is typically equal to Q over epsilon naught. But recall that with insulators, your charge will be charge per unit volume times volume of your surface. Or in other words, the thing I wrote on the top is rho. And recall rho is Q over V times the volume of your Gaussian surface that you drew. So what it's going to be is rho, which is charge Q, charge negative Q, divided by the volume of the Gaussian surface. The volume of the Gaussian surface. So recall for the volume for a sphere is 4 over 3 pi r cubed, right? So it's going to be 4 over 3 pi times the radius of the Gaussian surface, which is 3a cubed, but there is no charge in this hole, right? There's nothing in here. Our charge is only contained on the shell. So what we need to do is we need to subtract that hole in there. So that's going to be minus 4 over 3 pi, and that hole had a radius a, so a cubed. And this is going to be multiplied by our Gaussian surface, which is 4 over 3 pi arbitrary r cubed, because we're smaller than our radius 3a right now, right? Arbitrary r. And then we still need to subtract the hole in the middle. So minus 4 over 3 pi a cubed. So the only thing I can really simplify here is my 4 over 3 pi's will cancel out. So I pull out 4 over 3 pi. This would all go away. And then if I simplify the denominator, I have 3a cubed minus a cubed. This is what? 927 a cubed minus a cubed, which is 26 a cubed. So then I'm gonna have the electric field is negative q divided by this part. I'm dividing by this, right? So 4 pi r squared epsilon naught. And I'm gonna have r cubed minus a cubed divided by, what did I say? 26 a cubed. And then I can bring the 4 to the denominator. So I have negative q, or I'm going to pull out the 26 out to the times 4. 26 times 4 is 104. So I'm going to have 104 pi epsilon naught. And then now I'm going to distribute the a cubed is a constant as well. So let me pull that out, minus 1. And then I'm going to distribute my r squared. So r cubed divided by r squared is simply r. And then minus a cubed over r squared. And this is radially. So that should be radially inwards because it has a negative q. So if I solve for the potential now, because I don't need to solve, I'm not worrying about the outside of the sphere. I only care about a distance 2a. So if it did care about a point that was outside of the sphere, I would have to calculate that as well, which would just be q over epsilon naught, because when I'm on the outside, my radius, my arbitrary r would be the same radius as the volume of the shell, so they will both cancel out. So I'll be left with negative q or epsilon naught. So now, yeah, I'm just finding the difference. I have everything I need. So it'll be v of what? 2a minus from where? From the center. So v is 0. So that'll be the negative integral from 0 to a. It's 0. So I'm just not going to write that. But then from a to 3a, it's what we calculated. So it's going to be from a. But we're not going all the way to 3. We're going simply to 2a. So a to 2a of our electric field. Let me rewrite this actually. Let me pull out the constants and write the integral. So negative q over 104 pi a cubed of our integral from a to 2a of r minus a cubed over r squared dr. So negatives will cancel, right? So I'm left with q over 104 pi. Where did my epsilon naught go? There should be an epsilon naught. Epsilon naught a cubed times my integral. So that's r squared over 2 plus a cubed over r, right? From a to 2a. So when I plug in the bounds, I'm going to get 4a squared over 2 plus a cubed over 2a minus a squared over 2 plus a squared. This in here is 3/2 a cubed. This over here is 5 over 3 a squared, not cubed. I subtract these, I'm left with 2 over 2 a cubed, which is just 1. So I'm left with 8. Or I'm not sorry, I keep saying cube. It's a squared. 2 over 2 is 1, so I'm left with a squared. So in reality, I have q over 1 over 4 pi epsilon naught a cubed times a squared, which is simply q over 104 pi epsilon naught a. And that would be the answer for this question. So the main thing here is to remember that you need for insulators, it's charge divided by the volume of the actual shell, like the volume of the whole shell, times the volume of your Gaussian surface. And in this case, we needed to subtract the inner portion because there's no charge contained in there. It's all empty. The charge is only contained on the shell, so we subtract that empty part. Otherwise, we would get a wrong answer. So now, for number 4, a cylindrical shell. So it's important to know it's a cylinder. is made of a material with constant resistivity rho 1. The shell has an inner radius A and outer radius B. It is surrounded by another cylindrical shell. Okay, so we have two cylindrical shells here with inner radius B and outer radius F with constant resistivity rho 2. Okay, so it's not the same, it's changing. A battery with known voltage V is connected, as shown, so that a constant current is made to flow radially out from the inner surface to the outer. So what this is saying is that there's a current I flowing from the inner surface to the outer. So this is what it's saying. There's a current I. If I draw it over here as well. Current I flowing out. The length of a cylinder, the cylindrical shells are W, and we're asked to find the current. So what we're gonna use is, well, there's two ways to do this problem, and I'll show both right now. But typically we're gonna use Ohm's law, which is V equals IR. Resistance is rho L over A, and if we do it the other way, we will get the difference in the potential. So V of R2 minus V of R1 is equal to the negative integral of R1 of R2 E dot dr. And I'll show both ways. I'll do the first way right now. So the first way would be to calculate, actually, what does it want? It wants a current, okay. So we know current from Ohm's law is V over R. We already know what V is, so we do it the first way. We can just directly calculate R, and then we plug it in. So typically resistance is rho L over A, right? But in this case, my current is flowing radially out. So it's actually depending on where R is, because if I have like my current at this point is a little R, that's not going to be the same as if my R was at the red dot, or if my R was at the green dot, yellow dot. So what we have to do is we actually have to integrate over the radius. So in reality, we have dr is equal to rho. What is rho? Rho is rho for the smaller shell. So I should actually label this R1. So dr1 for a smaller shell is rho 1. My length changes with respect to R. So dr divided by the area of the cylinder. The area is 2 pi R times the length, or not, yeah, times the length of the cylinder. The length was said to be W times W. And then to find R1, you simply integrate both sides. So R1 is equal to rho 1 only exists from the shell A to B, right? So if I go back to my surface here, the resistivity is only for this portion. So I'm going to go from A to B of rho 1 over 2 pi R W dr. This gives me rho 1 over 2 pi W ln of B over A. And I got that because when I plug in my bounds, I get ln of B minus ln of A. I just use the property of logs to combine it. So now we're going to do the exact same thing for the second resistivity. So dr2, it's basically the same, just that rho is now rho 2. So rho 2 dr over the area, which is the same thing, 2 pi r. They both have a length W is what the question said. So it's W. And then I integrate both sides again. So R2 is equal to the integral. But now I need to see where is resistivity 2. The question says that the other cylindrical shell with radius B and outer radius F has a constant resistivity rho 2. So those are going to be my boundary integration. From B to F, it's going to be rho 2 over 2 pi RW dr. When I integrate, I get rho 2 over 2 pi W ln of F over B. Right? And then the total resistance of my cylinder would simply be the sum of those. So R1 plus R2, which is rho 2 over 2, oh no, rho 1 over 2 pi W ln of B over A plus rho 2 over 2 pi w ln of f over b. And I can simplify this a bit because they have the same, what's it called? They have the same, like, denominator. So I can have 1 over 2 pi w rho 1 ln of b over a plus rho 2 ln of f over b. This is my resistance total. And I note that V is equal to IR. I want a current, I is equal to V over R. I know what V is. I just solve for R. So I'm going to have the numerator, which is rho 1 ln of B over A, plus rho 2 ln of F over B, divided by the bottom, which is 2 pi W. So if I simplify this fraction, I get that the current is 2 pi WV over rho 1 ln of B over A. Let me write that better. One more space. I get I is 2 pi WV divided by rho 1 ln B over A plus rho 2 ln F over B. And yeah, that's what the answer key had. So that'll be the first way to do it. Now we do it the second way. I don't really have space, so I'm gonna erase everything here. But this is the correct answer. This is, again, your choice if you want to do the first way or the second way. But I'm gonna show you how to do the second way now. So just erase all of this. So the second way would be to find the voltage difference, the change in voltage across the whole cylinder. So that would be V of the length of the cylinder, which goes up to radius F, minus V of 0 would be the negative, and there'll be a bunch of integrals here. And for this method, we need to recall that the electric field is rho J, right? Where J is equal to the current divided by the area. And this case, again, the area is 2 pi RW. So my first region would be from 0 to A, right? But there's no charge close in there, so I'm skipping that. My next region would be from A to B, right? And my electric field is rho J. Rho for that region is rho 1. Rho 1 times J, which is a current, divided by the area, which is 2 pi RW. And then I'll add my second integral, right? Which is now going from B to F. And for that region, I have rho 2 now times current over the area, which is the same 2 pi RW. There should be a dr there. So when I take the integrals, I'll have negative rho 1 I over 2 pi W ln of B over A plus rho 2I over 2 pi W ln of F over B. And this would be V of F minus V of 0. But recall, to get the voltage, it will be the absolute value of this. So take the absolute value, so my negative goes away. So now I can say that V is equal to, I'm going to pull out the I. It's rho 1 ln of B over A. And they have the same denominator, so I'm going to add them together. So rho 2 ln of F over B over 2 pi W. And if we simplify this, we see that we get the exact same answer, because we're solving for current, so we divide on both sides. So I will be equal to 2 pi WV over rho 1 ln of B over A plus rho 2 ln of F over B. And that would be how to solve the current the second way, right? The voltage across the entire cylinder will be from the center to wherever the radius goes, which is F. Set that equal to V. Take your two integrals, divide by all that junk, solve for I, isolate I. and you'll get your answer. So I hope this was helpful to prepare for the exam, and good luck on your exam. Have a great day.